Back to my channel in J Math World. Due to the many requests of the students, I am here with the chapter graph, computational discrete mathematics, BSc first sem and second sem, first sem SCP and second sem NEP syllabus graph. So chapter 7, unit 4. So we are going to discuss completely about the chapter 4 today, that is chapter unit 4 and chapter 7. So in our discussion, we are going to discuss about definition of graph, undirected graph, introduction to graph, directed graph, basic terminologies of the graph, different forms of the forms of a graph, representation of graph, graph isomorphism, Euler and Hamilton path, Euclidean and Hamiltonian digraph, planar graph, short path problems, and graph coloring. So yeah, we have if we start with the discussion of a graph, we have application of graph. So what is mean by application? Application, where are this graph concept used in our daily life? So for example, we have social networking. In social networking, we have a social media platforms like Facebook, Twitter, LinkedIn, which represent the connectivity of the nodes and edges in the graph. How do we analyze? We analyze it by help of understanding social behavior, influence and trends of the social media. Okay, the next one you have is internet and web pages. The internet can be modelized as a graph with a web pages as node and hyperlink as the edges. So for searching in a Google, use graph algorithms to rank web pages and determine the most relevant results for given queries. Then you have next one is a recommendation of a system. So graph based recommendation system analyze user item interactions such as products purchased or movies watched to recommend new items. Collaborative filtering algorithm often use graph structures to find the similar user or items. Dermatology and disease spreads. What is this? Here we have modeling the spread of diseases like COVID-19 can be done using graphs. So how modelizing the spread of diseases, whichever types of disease which spreads in the overall the country, can be analyzed by using the graph, where individuals are nodes and interacting people become between the peoples are called as to be an edge. So graph based models helps in understanding the transmission dynamics and driving control strategies. Application of graph, we have different types of application in that. Another one is transportation networks. So here the connectivity of the node, that is road networks, subways systems and flight routine can also be represented as graphs with the cities or locations as nodes and roads, rails or flights as edges. So graph algorithm optimize routes, scheduling flights and plan public transportations. So we have all the connectivity which is connected to landway, airway and waterway is all learned, can be easily analyzed by using the graph theory. So yeah, next one you have is supply chain management. So here we have a supply chain management. It's nothing but manufacturing any one of the customer demand objects and item and supplying it to many. So how it is going to help here? So in a graph, so yeah, supply chain involves complex networks of suppliers, manufacturer, distributors and retailers. Graph help optimizing the flow of goods, minimum cost and manage inverters efficiencies. So next one you have telecommunication networks. So here we have telecommunication networks is nothing but internet, what we use communication networks and often represented using graph structures. Graph algorithm ensures efficiency routing of data packets and optimizing network performance. So whatever data, Wi-Fi, everything we use, it is also again a application of graph theory. So bioinformatics, for bioinformatics, we have genetics, molecular biology, and other way we will be using this graph. It is used to represent the relationship between the genes, genes and protein and biochemicals pathways. So graph algorithm is analyzed in DNA sequences, predicting protein interactions and understanding the disease mechanism in the body. Then you have urban planning. Urban planning is nothing but developing a new city, a rural city, into urban areas. So, such as city planning involving analyzing and relationship between the various entities like buildings, roads, park, and utilities, where all this can be planned by using the graph optimization, where it will be optimizing the land use, traffic flow, and infrastructure of developing the different ways to develop a new city. Then you have the last but not the least, you have a financial networks, where graphs are used in financial system to model a relationship between the entities such as a bank, investors, and assets, and transactions which is be going on in the bank. Graph algorithm detect the fraud, access risk, and optimize the investment portfolio. Then moving on with the chapter. So here we have what is mean by graph. That is what is mean by graph. Definition of a graph. The graph is nothing but it is a fundamental concept, is used to represent the relationship between the vertex and edges. Vertex. What is mean by vertex? Vertex is nothing but a node or a point, and edges are nothing but the lines and links. So here, if it is having a graph which is represented as vertex and edges, is called as graph in our sub chapter. So here the lines are called as edges. So we have 1, 2, 3, 4, and 5 edges. So we have edges are 5. So what is mean by vertex? Vertex are the points. We have how many points? 1, 2, 3, 4. So we have 4 points. So this graph is made up of 4 comma 5. What is 4? 4 is the number of points, that is vertex or vertices. Then E is the edge. Edge means line. How many edges we have? We have 5 edges. So usually the graph is represented as V comma E. Moving on with the next one, you have your directed graph, undirected graph, and directed graph. What is mean by undirected graph? Undirected graph is that one which has no direction. For example, when you are moving, when you are traveling in any road, highway road, you have the side service road. The service road is an example for undirected graph, where the person can go from there and he can return it from the same road. That is service road, which will be next to the highway. That is an example for daily life where we can see undirected graph. So here in a indirected graph, the edge do not have any direction, so you can go and come in the same path. So that is called as undirected. That is both the ways. The road which has both the ways uh, is called as undirected graph. So here there will be no direction given. Then next one is called as a directed graph, is also called as digraph. A directed graph, each edge has a direction and it is called U comma V is not as same as V comma U. In undirected graph, we can come from 1 to 4 and I can go from 4 to 1. But whereas in directed graph, there is only one way. I can go from 1 to 4 itself. I cannot go back to that place. So it's only U comma V will be there, but V comma U is not applicable for directed graph. They'll be given direction, so you can walk only with that direction. Is called as directed graph. So here we have 1 to 4 direction, 4 to 3, then we have only it is 1. Then if you go from this side, it is 1 to 2, then 2 to 3. Then if I go from here, there is 1 to 3. So to move from 1 to 3, we have a 3 different direction, that is 1 to 4 to 3. From 1 we are going to 4, and from 4 we will move on to 3. Then it is directly from 1 to 3 second road. Then we have the third one is 1 to 2 and 2 to 3. So these are the three different routes which we can travel from 1 to vertex 1 to 3. So moving on with the next one, we have is vertices and edges. What is vertex? Vertex is nothing but the point. Vertex is nothing but points. Edges are nothing but lines. So here we'll be finding how many vertex are there. They are 1, 2, 3, 4, 5, 6, 7. So how do we represent it? We'll write it in the form of set. 1 comma 2 comma 3 comma 4 comma 5 comma 6 comma 7. Then how do we write edges? Edges is nothing but the path which is moving from one node to other node. So it is from 1 to 2, so it gives it 1 comma 2, 1 to 2, then 2 to 3, then 3 to 7, then 7 to 6, then 6 to 5, then 2 to 4, then 4 to 5, then you have 3 to 4. So these are the edges, what how we represent it in the form of graph. Then moving on to the next one, we have basic terminologies of graph. What is mean by terminologies? We have different like adjacent vertex. What is mean by adjacent vertex? So adjacent vertex are the vertex that share an edge in the graph. If two vertex share the same edge, it is called as adjacent. So here 1 is adjacent to 2 and 3. 2 is adjacent to 2 is adjacent to 2 is adjacent to which one? 2 is adjacent to 1, 3 and 4. So 3 is adjacent to 1 and 2. Then 4 is adjacent to only 2. Then 5 has no adjacent vertex. The next one, you have adjacent in incident vertex. And incident vertex are the two vertex that shares the common edge. If it is having common edge, it is called as a incident vertex. So here we can see one is incidented with E1 and E2. E1 and E2 is incidenting to 1. We can write E1 and E2 are incidenting with 1. Then if I take here for 2, E1 and E3 is incidenting E1, E3 and E4 is incidenting to 2. So if I take 3, E2 and E3 is incidenting to 3. If I take 4, E4 only E4 is incidenting to 4. So the line which goes and touch that particular node is called as incident vertex or incident vertex. The next one is I have loop. What is a loop? Loop is nothing but a loop is an edge that contains a vertex to itself, and degree of the loop is always and in a is an undirected graph is defined as 2 where both ends are the same vertex. So ending and starting point of the loop edge will be same, then it is called as loop, and each value of the loop will be 2, starting point 1 and ending point 1. So it is the value of the loop will be 2, starting and ending point of a vertex when it is edge, when it is same, it's called as loop. Then you have degree. What is mean by degree? You will count how many lines are touching to that node. Count the number of lines which touch that node. For example, degree of the vertex is a degree of the vertex is an in an undirected graph is the number of edges. What is it? It is nothing but the number of edges that are incidenting to the vertex of the graph. So here if I take here for 4, how many edges are incidenting? 1, 2 and 3. So the incident vertex degree is 3. So if I take for 4, how many lines are incidenting? 1, 2 and 3. Degree is 3. If I take 1, it is 1 and 2. So 2 lines are incidenting. Degree is 2. 1, 2, 3. So the degree is 3 here. 1 and 2. The degree is 2. And for this, the degree is 1. So what is mean by degree? Degree is nothing but the number of edges that are incidenting to the vertex is called as degree. Next one you have. Now let us see, find out what is the degree of the given graph. For B, it is 1, 2, 2 degree. Here 1, 2, 3, 4. We have 4. What is the degree for here? 1, 2, 3. Then what is the degree here? 1, 2, 3. Then what is the degree for this? 1, 2, 3, 4. Then what is the degree? Here we have. Then you have 1, 2. For degree is 2. 1, 2, 3, 4. So degree is 4. 1, 2, 3, 4. It is 4. Then 1, 2, 3, 4. It is 4. 1, 2, 3, 4. It is 4. And it is again 1, 2, 3, 4. So here the degrees of the given vertex. Then you have 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And then 1, 2, 3, 4. So same way here 1 and 1, 2, 3, 4. 1, 2. 1, 2, 3, 4. 1, 2. 1, 2, 3, 4. 1, 2. 1, 2, 3, 4 and 1, 2. Now, next one is the handshaking lemma. What is mean by handshaking lemma? The sum of the degrees of the vertices of the graph is equal to the twice of the number of edges. The sum of the degree of the vertices of a graph is equal to twice the number of edges. So here the degree of the graph should be equal to 2 times of the edges. It's called as the handshaking lemma. That is, what is the degree of A? It is 2. What is the degree of D? It is 3. What is the degree of C? It is 2. What is the degree of D? It is 1. So you can just write 2, and B is, you can consider this as B. Okay, so B is 1, C is 2, and D is 3. So totally how much? 3, 4, 5, 6, 7, 8. So 8. So now you have other end is 2 into number of edges. What are the number of edges here? How many edges we have? We have here, so here we have number of edges, that is 1, 2, 3, 4. So totally 2 into 4, 2 4 is 8. So this and this should be same. If it is same means it satisfies the handshaking lemma. So here we have the some examples. The handshaking lemma is the total number of degree of the vertices should be equal to the number of edges. So here we'll just take A is how much? What is the degree of A? It is 1, 2, and 3. So 3. B is 1, 2, 3. Then C is 1, 2, 3. Then D is 1 and 2. Then E is 1 and 2. 1 and 2. Then F is 1, 2, 3. So here if you count 3 1 are 3 3 2 are 6 3 3 are 9 3 4 are 12. 12, 16, 18. So it is 18. So number of total sum is 18. Then it is 2 into what is number of edges. How many lines do we have here? We have to calculate the number of lines. So what will be number of lines here? It will be 1, 2, 3, 4, 5, 6, 7, 8. So it is into 8. 2 8s are 16. So they are not equal. Therefore it doesn't satisfy the Euler handshaking lemma. So here you have another one, minimum of all degree, which is minimum value. It is D and E. Which is maximum value? It is all that is A, comma B, comma C, comma F is all a maximum, maximum of all degree values. Okay. So next one, in degree out degree, the other formula in a directed graph, in degree of a vertex is defined as the number of incoming edges incidenting on a vertex A. Outgoing degree of the vertex is nothing but defined as number of outgoing edges from the vertex. So if the line is going away from the point, it is going out degree. If the line is coming inside it to the point, is called as in degree. So let us see what how many in degrees and out degree we have. So here first one, v1 we have 1 in degree. It is 1 in degree and 1 out degree. So it is 1 and 1. Then next one you have for V2. V2 is yeah. So we have out degree 1 and 2. So in degree is also 1 2, 2 and 2. Then next one V3. V3 is where V3 we have here. So we have 1 in degree and 1 out degree. So 1 and 1. Then you have V4. V4 is how much? You have 2 in degrees and 1 out degree. No? 2 in degrees and 1 out degree. Then for 5 it is V5 it is how many? It is out degree is 1, 2 in degree is 1. So in degree is 1, out degree is 2. So we are going to calculate this values. Now add them 2, 4, 5, 6, 7 and the other side 2, 4, 5, 6, 7. So always number of in degrees will be equal to number of out degree. It is another property of the graph. Then next one you have towards the node is called as in degree. The number of edges which is moving away from the node is called as out degree. So here, if the line is towards, the point, it is called as in degree. If the line is going out of that point, is called as out degree. So we'll just check how many in degrees and out degrees are there. We have a property which says number of in degree will be equal to sum of the in degree will be equal to sum of the out degree. So here according to that we have, here we have now we'll just take it for A. A is, we have how many in degree here? In degree is 1, 2 and 3. All the three lines are coming in. So it is 3. Then out degree from A we don't have any, so it is 0. Then for B we have a 1 in degree. It is 1 in degree and 2 lines are going out, so it is 2 out degree. Then next one we have C. For C we have 2 in degrees. 2 lines are coming in and 1 line is going out. So it is 1 out degree. Then for D it is 1 going, 2 and 3. All the 3 are going out, so it is 3 out degree. And here it is 0 in degree. So here if you calculate, if you add this, it will be 3 plus 1 4, 4 plus 2 is 6. So this will be 6. Then 2 plus 1 will be 3, 3 plus 3 will be 6. So always number of in degrees will be equal to number of odd degree according to the property. Then what is meant by isolated vertex? A vertex of a degree is 0. If there is no vertex to the node, then it is called as isolated vertex. So here if there is no edge to the point, then it is called as isolated. So here they are the example. Then we have pendant vertex. In a graph, if vertex has one or more only 1 degree, then it is called as pendant. If it should have only 1 degree, for example, here E is having only 1 degree. E has only 1 degree. One line is connected to E, therefore it is called as pendant vertex. Then moving with the next one, you have order of a graph. The number of vertices in the graph is called as order of the graph. The number of vertex means how many points we have, that is your vertex. So here we have 1, 2, 3, 4. So here it is 4. Then here 1, 2, 3, 4, 5. Here the vertex is 5. Then here 1, 2, 3, 4, 5, 6. Vertex is 6. Here 1, 2, 3, 4, 5. So it is 5. So here number of points are called as order of the vertex. Then you have size of the graph. What is mean by size of the graph? Size of the graph is the number of edges in the graph is called as size. So how many lines are there? We have to find. Edges means nothing but lines. So how many lines are there? We have to find in the graph. So you have 1, 2, 3, 4, 5, 6, 7. So here size is 7 for this graph. 1, 2, 3, 4, 5, 6. So the size of the graph is 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the size is 12. Here 1, 2, 3, 4, 5, 6, 7, 8. So here the size is 8. So number of lines in a graph is called as size of the graph. Then moving with the next one, you have degree or sequence of the graph. So what is mean by degree sequence? How many lines are joining to that point is called as degree. Degree sequence is nothing but arranging that degree in ascending order is called degree sequence. So here we will take it for A. It is 1 and 2, 2 lines. So here 1, 2, 3, 4, 4. Then here for C, 1, 2, 3, 4. Then for E, it is 1, 2, 3, 4. Then for F, 1, 2, 3, 4. Then for G, 1, 2. And then it is for D, 1, 2, 3, 4. It is 4. So arranging it in order, that is called as degree sequence. That is 2, comma 2. And we have 4 5 times. 1, 2, 3, 4 and 5. Then moving with the next one, if I take this as A, B, C, D, E, F and G. So yeah, what will be the degree sequence for this? If I take this as A is 1, 2, 3, B is 1, 2, 3, C is 1, 2, 3, D is 1, 2, 3, E is 1, 2, 3, and F is also 1, 2, 3. And G is 1, 2, 3, 4, 5, 6. 6. So here the degree sequence will be 3. How many 3s? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And 1, 6. And the last. So this is called as degree sequence. So here next one we will take. I'll consider these points as P, Q, R, S, T. So we'll just find what is the degree sequence of this. So yeah, let me take for P 1, 2, 3, 4. Then here Q 1, 2, 3, 4. 4 lines. Here 1, 2, 3, 4. 4 lines. 1, 2, 3, 4. 4 lines. 1, 2, 3, 4. 4 lines. So here the degree sequence of this will be 4 comma 4 comma 4 comma 4 comma 4, 5 fours. So next moving on with there 1 1 2, and there 1 2 1 2 1 2 1 2 1 and 2, then 1 and 2. So here 1 2 3 4 5 6 7. So the degree sequence will be 1 2 3 4 5 6 7. Then here next one 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3, 3 lines. So here center one 1 2 3 4 5. So it is 5. So it will be 3 comma 1 2 3 4 5, 1 2 3 4 5, and then 5. So this is called as degree sequence of the given graph. Then moving on, the next one is called walk. What is a walk? A walk is a sequence of vertices or edges of the graph. It is a sequence of edges and graph. For example, here we have 1 to 2, 2 to 3, and 3 to 4, and 4 to 2, and then 2 to 1, and 1 to 3 is a walk. Okay. So here we are moving in the sequence of a lines, sequence of vertices and edges of the graph. So it is represented as V0, E0, V1, E1, V2, E2. So that will be written as 1 to 2, 2 to 3, 3 to 4, 4 to 2, 2 to 1, and then again to 3. Walk can be open or closed. Length of the walk here is 1, 2, 3, 4, 5, 6. So 6, it is here. How many edges are there? You have to check. 1, 2, 3, 4, 5, 6 edges. So here the walk will be 6. Okay. So you have an open walk and you have a closed walk. What does it mean by open walk? A walk is said to be open walk if the starting and ending vertex are different, and the original vertex and the terminating vertex are different. In a closed walk, a walk is said to be a closed walk if the starting and ending vertex are identical, same. So, for example, open walk is 1 to 2, 2 to 3. So, if I take here 1 to 2, 2 to 3, 1 to 2, 2 to 3, 1 to 2, 2 to 3, then 3 to 4, 4 to 5, then 5 to 3. So here this is called as open vertex. So open vertex means it is starting and ending points are different. Then if you take the next one, it is from 1 to 2, then 2 to 3, 2 to 3, then 3 to 4, 4 to 5, 5 to 3, and 3 to 1. So the starting and ending point is same. It is called as closed walk. The next one is called trial. What is meant by trial? Trial is an open walk which no edge is repeated. The edge should not repeat. We should not go to the same edge, and vertex can be repeated. We can repeat the vertex, but edge vertex means points. We can repeat the points, but lines should not be repeated. For example, here it is from 1 to 3, 3 to 8, 8 to 6, 6 to 3, then 3 to 2. So here we are walking from 1 to 8, 8 to 6, 6 to 3, then 3. So here vertex is repeating, but edges are repeated only, gone through edges only one time. Okay. So and the end point, if we move back to the starting and ending point is same, it is called as closed trial. Then you have next one, path. What is mean by path? If a trial in which either vertex nor edges are repeated, neither edge should, vertex means path means neither the edge should repeat nor the vertex. So here we start with 6, 6 to 8, 8 to 3, 3 to 1, 1 to 2, and 2 to 4. So here we can see there is no edge nor the vertex is repeating. So such a walk is called as path. So next one, you have circuit. What is mean by circuit? Traversing a graph such that not an edge is repeated, but a vertex can be repeated. Traveling a graph where a edge should not repeat, but vertex can repeat. Vertex means point can repeat and edge should not be repeated. So here we can take from 1, 1 to 2, 2 to 4, 4 to 3, 3 to 6, 6 to 8, 8 to 3, 3 to 1. So is a circuit which is a closed trial, or it is also called as circuit. This can have a repeated vertex only. Vertex can be repeated, but edges should not repeat in a circuit. Then next one, you have cycle. What is mean by cycle? Traveling a graph such that we do not repeat an vertex nor we repeat the edge, but the starting and ending vertex must be same. If starting and ending vertex is same and we do not repeat any vertex twice and edges twice, is called a cycle. For example, we start from 1 to 2, then 2 to 4, then 4 to 3, and then 3 to 1. This is called as cycle. So here cycle can be defined as the closed path where vertex should not repeat and edge should not repeat. So here we have a closed path. Cycle is a closed path, and here they cannot repeat any edge or vertex. Note the closed sequence starting and ending vertex are the only ones that can be repeated. Starting and ending point can repeat, but others we should not repeat in a cycle. Then next one, you have a table for this walk. Edge can repeat, vertex can repeat. Then in trial, edge cannot repeat, vertex can repeat. Then in path, edge cannot repeat, vertex cannot repeat. Okay, you can see walk and path has the same. Here it can repeat. Here cannot repeat, can repeat, and there both they cannot repeat. Then these are the conditions for having a walk, trial, and path. Now next one, type of the graph of different forms. We have different forms of graph. So here we have first one is called simple graph. What is mean by simple graph? A graph is called a simple graph if the graph is undirected, does not contain any self loop, and multi edges. So here it should be very simple graph, means it should have no self loop or it should not be having any multiple edges. Then it is called as simple graph. Then multi graph, a graph having no loop, self loop, but having parallel edges in it is called as multi graph. For example, you can see here you have a not self loop, but it is having a multi, that is parallel edges. Then it is called as multi graph. Then next one, you have types of graph. In the next one is pseudograph. What is meant by pseudograph? A graph which having no parallel edges but having a self loop. It should have a self loop, but there should be no parallel edges. There should be no parallel edges, but it can have a self loop. So it has a self loop, and it has a self loop. A graph having self, no parallel edges, but having a self loop is called as pseudo. So here it should not have a parallel line, okay, but it can have a self loop. Then it is called as a pseudo graph. So here this line should not be there, okay. Then what is mean by null graph? A graph whose edges set is empty. That means if there is no edge, then it is called as null graph. A graph whose edge set is empty and is called as null graph does not contain any edge. If there is no edge, it is called as null graph. Then you have next one is trivial graph. What is mean by trivial? A graph having only one vertex. If it has only one vertex, it is called as trivial graph. Then you have subgraph, a graph whose vertices and edges are the subset of another graph. If it is having a subset of another graph, for example, if I take this, is a subset of this graph. No, so here subset is nothing but a graph whose contain vertex and edges similar to that of the graph is called as subgraph. Then you have complete graph. What is mean by complete graph? A simple graph is said to be complete if every vertex in G is connected with every other vertex, and the formula for that is Kn equals n into n minus 1 divided by 2. So here that is complete graph for 2, 3, 4, 5 nodes are. So it is here 1. Then here it should have what? It should be complete graph. Every vertex should be connected with every other vertex. So every vertex should be connected with every other vertex. Then it is called as complete graph. And this points are called as K1, K2. If 2 point means K2, 3 point means K3, 4 point means K4, 5 point means K5, and it goes on. Okay. So it will be 1, 2, 3, 4, 5, 6. Then for the 6 you have to draw the graph. Okay. Then here it is 7, K7. K7 is 7 points. So you have to draw this. So it's called as complete graph. If a simple graph is said to be complete if every vertex of G is connected with the other vertex is called as complete graph. Then you have regular graph. What is meant by regular graph? A simple graph is said to be regular if all the vertices of the graph are equal degree. So here we have to find 1 2 equal degree 1 2 1 2 and 2. If the degree is set same 1 2 1 2 1 2. If degrees are same, it is called as regular graph. 1 2 3 1 2 3 1 2 3 1 2 3. Sign. So here next one is connected graph. A graph is said to be connected in the an undirected graph is called as connected if every pair of vertex there exists a path between them. If there exists a path from I to J, the path should be from J to I. It is called as strongly connected. So you have here if it is point A for it should be connected from 2 to 4. Okay, for connected graph. If it is strongly connected, you should have one both the ways. Okay, then it is called as strongly connected graph. Then you have disconnected graph. If a graph which has no does not exist any path between at least one pair of the vertex. So here there is one vertex and here there is no connection, then it is called as disconnected graph. Then you have next one is weight graph. What is weight graph? A weighted graph undirected for directed G consists of the set of vertices of the vertex and set E edges of the edges, and weight are the assigned to every edges. So here we can see this is a 20 30. We can see from one place to another place traveling we get how many kilometers. We can consider that to be weight. Okay. Then next one you have is cycle graph. What is meant by cycle graph? A graph G consists of a vertex and which is greater than or equal to 3. That is called as cyclic graph. So it should be greater than or equal to 3, then only it is called as cyclic graph. So here you can take this is as example for cyclic graph for 3 points, for 4 points, for 5 points, for 6 points. Then moving on with this next one you have wheel. What is mean by wheel? A graph formed from a cycle graph by adding a new vertex adjacent to the vertex in the cycle. So here is in the cycle. So here we have cycle 3 by 3. So you have to take this and connect it with the center one point. So here you have 4. So 4 points. You have to draw one point in the center and join all the 4 here. Same way for 5, you have 5 points. You have to draw a point and join all the 5 points in the center. So that way you will be finding it for wheel of a graph. Then next one you have acyclic graph. What is acyclic graph? A graph not containing any cycle in it is called as acyclic graph. So it is not connected. Suppose if I draw this, it will become a cycle. That there is no line between them. And here also, if I draw, it will become a cycle, but there is no connection. Then it is called as acyclic graph. So cyclic means it will be closed for all from all the parts. Acyclic means there will be no line which will connect the all the vertex. Okay, every vertex will not be connected with every other vertex. Then finite graph. What is finite graph? A graph containing a finite number of vertex is called as finite. So we can count 1, 2, 3, 4, 5. So 5 points are there, therefore it is called finite. So here infinite means here 1, 2, 3, 4. It is still continuing. So here there is we cannot take a count of a vertex or edges. That is called as infinite graph. Then you have planar graph. What is planar graph? A planar graph is a graph. A planar graph is a graph that we can draw in a plane such that no two edges of it cross each other. So no edges should cross each other. If it is crossing, it is not a planar graph. For example, you have here there is an edge which is meeting to this point. So what we can do is we can draw this as So this connection line we can take and give it from outside. And for this also you have planar. So one line we will remove from here. Any line you can remove. I'll keep this line as it is. The other line I'll take from here to here. I will join. Okay, that is called planar graph, where the edges should not cross each other. Then you have bipartition graph. What is bipartition graph? Graph of a two disjoint set in which every vertex of one set is connected to at least one of the other. Also is known as the vertex belonging to the same set to join each other. See here you can see bipartition means B A you have, then B you have, then A one more you have, then so yeah, if it is 1, 2, 3, 4, 5, 6, we can write this separately. We can connect them 1 to 2. Then you have 2 to 3. Then you have 3 to 4. Then you have 4 to 5. Then you have 5 to 6. And then you have 6 to 1. So it is called as bipartition graph. Then you have next one. Types of graph and Euler graph. What is mean by Euler? Euler. Euler graph is connected graph in which all the vertices are even degree. So let me check 1, 2, here 2, 1, 2, 2, then 1, 2, 3, 4, then 1, 2, and then 1, 2. So it is leaving C is 4, the remaining all are 2. So all are even degree, it is a Euler graph. Then next one, A is 1, 2, 3, 4, B is 1, 2, C is 1, 2, D is 1, 2, 3, 4, E is 1, 2, and F is 1, 2. So all are even, therefore it is Euler. Then Euler. Then we'll go for this 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 6. So it is how much? It is 5, 5. No, and D1 is 6. So it is D is 6, remaining all are 3, 5. So it is not a Euler because the answer we got is not even. Then the next one is 1, 2, A is 2, B is 1, 2, 3, 4, and C is 1, 2, 3, 4, D is 1, 2, 3, 4, and E is 1, 2, 3, 4, and F is 1, 2, 3, 4. So here all are even degree, therefore it is an Euler graph. Then next one is Hamilton graph. What is Hamilton graph? A Hamilton graph is a graph that has a cycle containing all its vertex. A cycle that visit every vertex exactly once and return to the starting vertex is called Hamiltonian graph. So we start from one point and visit all the vertex and we come back to that particular place. It's called as a Hamiltonian graph. So if I take V1, if I'm going to V2, V3, and then I'm coming back to V1. So if I take A to C, C to B, D, E to D, D to C, C to A, and then A, then it is coming and ending, starting and ending point should be same, and it should attain all the vertex, all the edges. It should go to all the edges. Then you have directed acyclic graph. What is directed? A directed acyclic graph, DAG, is a digraph, that is directed graph which has no cycle. If it is having no cycle, it is called as directed acyclic graph. So if I take for, you can see here, if I start from here 1, then I can go to 6, then 5, then I don't have any connectivity, it cannot be completed. So if it has no cycle, then it is called as directed acyclic graph. Then you have next one is Platonic graph. A Platonic graph are the set of graph representing the edges and vertices of 5 regular Platonic solids. So here you have tetrahedron, octahedron, cube, decahedron, and isosahedron. So these are the 5 examples for then representing of the graph. So we can represent the graph into 3 different ways. One is adjacence matrix, incident matrix, and adjacency list. So here what is mean by adjacent matrix? Adjacent matrix is a square matrix used for the representing of finite graph. The element of the matrix indicate whether the pair of the vertices are adjacent or not. So here we can say if from A to A, how many lines are there from A to A? I do have no lines. So from A to B, yes, I have one. From A to C, I have one. From A to D, I have one. From D to E, I have no, zero. So then from B to A, you can take from B to A. If I take from B to A, it is B to A 1, B to A is 1, B to B is 0, B to C is no 0, B to D is 1, 1, B to E is 1. So here next one, you can go for C, then C. From C to A we have 1, C to B we don't have 0, C to C we don't have self loop, C to D we have 1, and C to E we don't have 0. Then go for D. From D to A we have 1, D to B we have 1, D to C we have 1, D to D we have 1 self loop also, and D to E is also 1. Then going for E, we have E is A to B, E to B 1, then E to D 1. The remaining all are 0. So this is the way how you represent the adjacent matrix by given graph, by using the data which is given in the graph. Then you have, if there is an edge between the vertex, it is 1, and if there is no edge, it is considered to be 0. So here let me check out. A to A I have no edge, it is 0. A to B we have 1 edge. A to C we have 1 edge. A to D we have 1 edge. And A to E we have no edge, so it is 0. Then going with the next one, we have B. From B to A, from B to A we have 1. B to B we have 0. B to C we have no edge. B to D we have 1 edge. B to E we have 1 edge. Then moving on with the next one. Next one, if you take C, from C to A. C to A we have 1. C to B we have no edge. C to C we don't have self loop. C to D we have 1. C to E we have no connection. Then we'll go for the next one. It is D to A, D to A. D to A we have 1. D to B we have 1. D to C we have 1. D to D also we have 1. And D to E also we have 1. Then moving with the next one. It is E. So E to A we have no 0. E to B we have 1 line. E to C there is no connection. E to D we have 1. E to E we have no self loop. So this is how we represent the matrix that can be written as 0 1 1 1 0, 0 1 1 0, 0 1 1 1 0. It is 1 0, yeah. It is next is 1 0 0 1 1. That is 1 0 0 1 0. Then 1 1 1 1 1, and then the last one 0 1 0 1 0. So this will be represented as matrix. It's called as adjacency matrix. Then moving on with the next one, the same here, if it is directed matrix. So we have to check out the direction. A to A we don't have anything, so it is 0. A to B, yeah, it is going 1. A to C, yeah, we have 1 connection. Then A to D, there is no line which is moving from A. Then A to E also we have no connection. Then directed we are going with the next one. It is B. B to A we have no connection, 0. B to B also we don't have self loop. B to C also we don't have anything. Then B to D it is going 1. B to E also it is going, it is 1. Then moving with the next one, you have C to A. C to A we have no 0. C to B also we have no connection. C to C no self loop. C to D we have 1. Then C to E we have 0. Then we'll go with the next one, that is D. So it will be for D. D to A, yes, we have D to A, it is going 1. Then D to B, it is no 0. D to C, no 0. The line should go out, then it is considered as 1. Then D to D, yes, we have a self loop. Then D to E, yes, we have 1, it is going 1. So yeah, next one we consider, next one is E, that is E to A. E to A we have no nothing, 0. E to B we don't have anything. Then E to C also we don't have any line. E to D also we don't have any line. Then E to E also we don't have a self loop. So this is a adjacent matrix for the directed graph. We write it 0 0 0 1 1 0 0 0 1 0. So 1 0 0 1 1, then 0 0 0 0 0. So you can check here one difference we can find. So in this connected graph, okay, it is directed graph. We have how many path, how many ways we have? 1 2 3 4 5 6 7 8. Okay, the same if you move on with the next one, here undirected graph we have how many? It is 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. We have 15, one more 15, and a self loop. Here it is D to D here, and yeah, so it will be double of the directed graph. Here we have 6, and that will be 1 2 3 4 5 6 7 8. 8 into 8 16, it should be 16 over here. Okay, it will be double of that. So where we have missed it anything? A to A to B, and A to C. A to C, it is A to C. We have, yeah, A to D, yeah. Then A to E we don't have. Then B to A, yes, 1. B to B, 0. B to C, 0. B to D is 1. Then B to E is also 1. Then C to 1, C to A is 1. C to B is 0. C to C is 0. C to D is 1, and C to E is 0. Then D to A is 1, B is 1, C is also 1. Then it is C to D is also 1, D to E is 1. Then you have E to A is 0, E to B is 1, E to C is 0, E to D is 1, then E to uh, B to D, okay, E to E is a 0. So here self loop we can consider as 2, therefore it will come here. If it is 8, the other one will be 16. Directed graph will indirected graph will have double. That is, if a directed graph have 8 edges, the undirected will be having 8 into 2, that will be 16 edges. Okay, so for the self loop you can consider here as 2. If I take a self loop, that is D to do as 2, then it will be total how many ways? It will be 18 ways. So yeah, next one is moving on to the next one. We have next is for this we will just check adjacency matrix for with weight. Adjacency matrix with weight. Okay, so in place of number we should write the weight of this. So here, if it is having a weight, then it is written, the weight value is written in the place, and then if it is having no weight, it is written as infinity. Okay, so here we'll just start 1 to 1. We have no loop, so it is infinity. Then 8 1 to 2, it is 5. 1 to 3 we don't have. 1 to 4, 1 to 4 we have 6. 1 to 4 is 6. Then 1 to 5 is 10. 1 to 5 is 10. The remaining we don't have, it will become infinity. Then next one, we'll take next one. It is for 2. From 2 to A1 we have 5. 2 to 1 is 5. Then 2 to 5, 2 to 3 is 1. 2 to 3 is 1. Then 2 to 5 is 2. 2 to 5 is 2. Then 2 to 6 is 7. 2 to 6 is 7. Then that's it. So we have the other ones are, the remaining ones will be infinity. Then next one is, we'll go for the line 3, that is 3. Where is 3? Here we will consider 3. So from 3 to 2 is 3 to 2 is 1. 3 to 6 is 8. 3 to 6 is 8. The remaining we don't have, only 2 lines, so it is infinity. Then we'll go for the fourth one. We will go for fourth line, that is here fourth one. So from 4 it is 5, it is 3. 4 to 5 it is 3. Then 4 to 1 is 6. 4 to 1 is 6. So only 2 lines, the remaining all will be infinity. Then next one you have is 5. For 5 it is, from 5 it is 5 to 2 is 2. 5 to 2 is 2. Then 5 to 4 is 3. 5 to 4 is 3. Then 5 to 1 is 10. 5 to 1 is 10. Then 5 to 6 is 4. 5 to 6 is 4. The remaining will be infinity. Then the next one is 6. So from 6 it is 6 to 2 is 7. 6 to 2 is 7. 6 to 3 is 8. 6 to 3 is 8. 6 to 7 is 4. 6 to 5 is 4. So we have only 3 lines, so the remaining will be infinite. So this is a weighted graph matrix with undirected weighted graph. It's undirected weighted graph. Okay. So we'll move on with the adjacent matrix, that is directed weighted graph. How do we write directed weighted graph? Again, it's the same. So yeah, we can consider A. From A it is going to B, it is 3. Then from A it is going to 6, it is 5. E, it is 5. Then next one, we go with the next one, it is B. From B, from B to E it is 3. From B to E it is 3. Then from B to C it is 8. B to C it is 8. Then B to D it is 5. B to D is 5. Then we don't have, only 3 lines here, which is going out from that point. Then we'll go for the next one. It is C. From C we have no connection. That is, no line is going out, so it will not be considered. Okay. So yeah, next one is next point is, if from here it is a C. From C, where is C here? It is C. That is nothing. Then we'll go for the D part. D. From D it is going to C. One C. It is D to C. It is 2. The remaining we don't have. Then we'll go for E. And E is going from E to D. It is 4. E to D is 4. Then we have just completed for all. The remaining will be infinity. If there is no line or edge which is going from one vertex to other vertex, then we'll write it as infinity. So this is directed weighted graph. Okay. Then moving on with the next one, advantages of adjacency matrix. It is easy to implementation. Implementation is easy. Fast edge lookup. We can check the edges between the two vertex. Efficiency for the denser graph. The number of edges is close to n square. We can check them. Uniform space usage. So uniformly the space can be used. Supports weight graph. It has a supporting a weight graph. Then disadvantages: high space usage. So we need to give a more space for that. Inefficiency for the sparse graph. That is, space for the graph with a small number of edges is not possible. Edges iteration is costly. Repetition of the method is costly. Less dynamic. So difference to modify. It is very charges frequently if you are changing the dynamic. That is a method of working. Then memory intensive for large graph, so memory should also be more for the graph. Then you have next one is called incident matrix. What is mean by incident matrix? Incident matrix is defined as the matrix representing a graph with rows for vertex and columns for edges. The entries in a incident matrix are +1 for incidenting edges, and 0 for no edges, and -1 for the edges which is going outside. Okay, so here it is for undirected graph. If it is incidenting, it is 1. If it is no edge, it is 0. Okay, so how do we write? We will go for edge 1, v1. So here v1, see which are the lines which are connected, e1 and e2. So e1 and e2. So for then for 2, if you go, it is e2 and e4, e2 and e2 and e4. The remaining will be 0. The remaining will be 0. Then e2 4 0. Then third one, it is 3. It is e4, e5, e4, e5, e8, e9, e8 and e9. The remaining is 0. 1 2 3 4 5. Then if you go for 3 4, we have e1 and e3 is incidenting, e4, e1 and e3. E3 is incidenting. Only 2 lines. So the remaining is 0. Then for the next one, e5, we have e3, e5, e6, e3, e5, e6. The remaining will be 0. Then next one, for e6 there is only one, that is e9. E9 is 1. The remaining all are 0. Then for e7 it is e8 and e7, e7 and e8. It is e7 and e8. The remaining will be 0. So which are the edges which are incidenting on that particular vertex? We should write e8, it is only 2, e6 and e7. The remaining all are 0. So this is called incident matrix of a given graph. Hope you people have understood. You can take a break and come back, students. If you feel tired, you can take a break, refresh yourself and come back for the continuation of the video. You can pause and you can go take a break and come back. Okay. Then yeah, we have incident matrix of a directed graph. What is mean by directed graph? If the entries in an incident matrix are -1 for incoming branch. If it is coming inside, that is if it is moving towards the node, it is -1. +1 if it is going out, and 0 for others. If there is no edge, it is a 0. If it is going out, it is +1. If it is moving towards the point, it is -1. So here we'll take for A. So for A, 1 and 2, E1 and E2 are going out. So if it is going out, it is 1. And E3 is coming in. If it is coming in, it is -1. The remaining edges are not there, so it will be 0. Then for B, if I take it for B it is E4 and E6 are going out. E4 and E6 are going out. Then E1 is coming in. E1 is coming in is -1. There are only 3 edges connected, so the remaining one will be zeros. Then for C, it is 1 going out, 1, that is E5 is going out, 1, and E2 is coming in. Whenever it's coming in, -1. So the remaining will be 0. Then the next one for D is so E5 and E4 is coming in. E5 and E4, E5, E4, and E8 is also coming in. So we have, I've not written here 8. So E8 here it's coming in for D, it's -1. So the lines which are going out is E7 and E3. E7 and E3. E7 is 1, E3 is 1. The remaining will be 0. Then the next one is for E. For E, it is It is two lines are coming in E6 and E7, that is minus 1. E6 and E7 is minus 1, the remaining all are 0 because it's not connected. So this is how you draw a incident graph for the given matrix when the direction is given. Okay, incident matrix of directed graph. Hope you people have understood. We'll move on to the next one. Then you have adjacency list. What is mean by adjacency list? In a graph, we maintain the list of its neighbors. It means every vertex of a graph contains list of its adjacent vertex. An array of vertex which is incidented by the vertex number, and for each vertex v, the corresponding array element point is to be slightly linked list of neighbors of v. So you have pros, which is adjacent list saved for a lots of space. We can easily insert or delete as we use a link list. Such kind of representation is easy to follow and clearly shows the adjacent nodes of the node. Cons means the adjacency list allows testing whether two vertices are adjacent to each other, but it is slow to support this operation. So here we have, for example, adjacency list for the undirected graph. You can see here 0, 1, 2, 3, 4. So which are the adjacent for 0? It is 0 is 1, 2 and 4. So for 1 is 2, 2, 0 and 4. So for it is 2, it is 1, 0 and 3. 0, 1, 3. Then for 3 it is only 2. Then for 4 it is 0 and 1. So these are the adjacent list. Okay. Then you have for adjacent list for the undirected graph. So for directed graph, adjacency for 0 is only 1 and 2. Then for 1 is 2. Then for 2 is only 3. Then for 3 is only 1. So it is called as adjacency list. Then adjacency list, you have advantages and disadvantages. Space efficiency, fast edge iteration, dynamic nature, efficiency storage, adaptable to weighted graph. Disadvantages will be slow edge lookup, that is existing of two vertex is the worst in a worst case. Inefficiency for dense graph, it cannot be operated for the dense graph, we cannot travel. Extra memory for pointers it requires. Then complex implementation is very difficult. Not ideal for matrix based algorithms, so it is not useful for matrix based algorithms. Then you have next one is this important topic, graph isomorphism. What is mean by graph isomorphism? Graph isomorphism means two graph are essential the same in the structure, even if they look different, or the graph can be redrawn to look identical without changing their connections. The isomorphism graph can be defined as the graph in which a single graph can have more than one form. So these are the two different types of isomorphic graph. So we have some condition for isomorphic graph. What are the four conditions? We have four conditions. G1 and G2 are said to be isomorphic if number of vertex in both the graphs are same. Then the number of edges in both the graphs are same. Then the degree sequence of both the graph must be same, and it should be written in ascending order. Then if the first graph is form of cycle, the length of k with the help of vertices, then the other graph must also form the same cycle of the same length k with the help of the vertices. So that is nothing but the length of the cycles in the graph should be same. You can write length of the cycle in the graph should be same. Then graph isomorphic, the graph are surely isomorphic if it satisfy the following condition. Two graph are isomorphic if and only if their complement graph are isomorphic. Two graphs are isomorphic if their adjacency matrix are same. Two graphs are isomorphic if their corresponding subgroup obtained by deleting some vertex of the one graph and their corresponding images in the other graph are isomorphic. For here we will just find it is isomorphic or no. So here we will just see here number of vertex in the G1. Vertex is 1, 2, 3, 4. So vertex is 4. Here also we have 1, 2, 3, 4. So it is 4. Then number of edges, lines 1, 2, 3, 4, 5. 5 lines. Here 1, 2, 3, 4, 5. It is also 5. Then you have degree sequence. We'll just see degree sequence. Here the degree is 3, here the degree is 2, here the degree is 3, and here the degree is 2. So we can write it as 2 comma 2 comma 3 comma 3. For this it is 1 2 3, then 1 2 1 2 3, and here 1 2. So it is also 2 comma 2 comma 3 comma 3. Now if you take the cycle of one graph, it should have the same vertex. Number of vertex, length of the vertex should be same. So if I take here, if I take from here 1 2 3 4, I'll take here 1 2 3 1 2 3 4. So here also we have 4 4 4. Length of the cycle is 4 and 4. Then if I take the small one, it is 1 2 and 3. I'll take for this also 1 2 and 3 this side. So here the length of the cycle same, therefore it is 4 and 4, and then it is isomorphic. The second one we'll check. They are 1 2 3 4 vertex. Then here also 1 2 3 4 vertex. Then here edges are 1 2 3 4 5. Even here 1 2 3 4 5, 5 edges. Then degree sequence will be, the degree sequence will be for this, it will be degree sequence will be 1 2 1 2 3 1 2 1 2 3. So it will be 2 comma 2 comma 3 comma 3. So here 1 2 1 2 3 1 2 1 2 3. So it is again 2 comma 2 comma 3 comma 3. Then the length of the cycle, it should be same. We'll just check length of the cycle is same for both the graph. If it is same, then it is isomorphic. So here length of the cycle, here it is 1 2 3 4. Here also I can take 1 2 3 4. It is same 4 4, one cycle. Second one I'll take, I may take 1 and 2, the other cycle 1 2. So I can take this 1 2 3. But here if it here it is 2 and here it is 3, the cycle is not same. Therefore it is here 2 and here it is 3. Therefore it is not isomorphic. It is not isomorphic. If any one of the condition does not satisfy, it is not an isomorphic. To prove isomorphic, so here we have to find how many number of vertex. 1 2 3 4. We have 4 vertex, and in the other one is also we have 1 2 3 and 4. 4. Then here edges are 1 2 3 4 5 6 edges. So here it is 6 edges. Here also 1 2 3 4 5 6 6 edges are there. Then the degree sequence of both the graph, if you take, it is the degree sequence is here 2, then here 3 3 4. So here 1 2 3 4 1 2 3 1 2 3 and 1 2. So you can take here it is 2 3 3 4, and here also we have 2 3 3 4. Now if you take a cycle in this graph, that is we have to just connect from one mapping of this, we have to do from one graph to other graph. Suppose if I take this as A B C, if I take it as A B C D, and here P Q R S. So we have to check out the mapping of this. Now suppose if I take D, if I take A, so A is connected with the 2 edges, and here it is connected with 3, and this is connected with 1 2 3 4. So A can be mapped with either B means if I'm mapping with the B, so it will be A is how many? 2. So you select where is 2. Here we have, this can be taken as 2. So yeah, you have to, I'm connecting with the B. So B means here it will be connected with B. One should have 4 and one should have 3. 2, 3, 4. So yeah, it is having 4, and here the other side is having 3. So here A is mapped to yes. Then if I take the next one, because A and S is having the same alternative degrees with the next vertex. Then if you take the next one, then if you take A, B, C, D, and here also A, P, Q, R, S. Now if I take this R should be mapped with, R is having first 3 degree. So here R we can, and then it is connected with the 2, and the other side is 1, 2, 3. So you have to check if I'm taking this B as a B is mapped with the R, then it should have 1, 2, 3. Yeah, it is having 3, and the other side should be 2. So here B and R are mapped. Then next one, if you take the next one, it will be, so we have connected this two. So we'll go for the next one. So here next one we have done with this A and S. Then we have done with R and B. Then you have next one is C. If I take C, it is 1, 2, 3 degree. Then when which is connected, it is 1, 2, 3, and here 1, 2, 3, 4, 4 we have. So here it is taken as the one which is connected. So we have done with this two. So I'll take this one. 1, 2, 3. It is 3. Then it's connected with 1, 2, 3, 4. Okay, 4. And the other side is also 3, and it is connected with the 4 and 3. So it is 1, 2, 3. So 3. So we can take C and map with the Q. The last one will be the remaining one, which is D will be mapped with we have P. D and P. D will be mapped with P. So here, what is the length of the cycle? The length of the cycle is nothing but number of edges, okay, which is formed by the cycle. So now suppose I take in this number of length of the cycle here, it is here, it is if I take this cycle 1, 2, 3 and 4. Even if I take this 1, 2, 3, 4. So it can be 4 and 4. No? If I take the other cycle, that is, if I take the other one, it is 1, 2, 3, 4. If I take here also, it is 1, 2, 3 and 4. So here the length is also 4. Therefore, it is an isomorphic. Then moving with the next one, you have mapping. I have explained you. The next one is for this you have how many vertex? 1, 2, 3, 4, 5, 6, 7, 8. We have 8. Here also 1, 2, 3, 4, 5, 6, 7, 8. We have 8. Then edges are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 edges are there in here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You have 10 edges. Then degree sequence. If you check with the degree sequence for the first one and the second one graph, you get, so yeah, it is 1, 2, 3. Then here also 1, 2, 3. Then here 1, 2. Then here 1, 2, 2. Then here 1, 2, 3. Then here 1, 2, 3. Then 1, 2. Then 1, 2. So here today 1, 2, 3, 4. That is 2, 2, 2, 2, 4 times. Then 3, 1, 2, 3, 4. 4 times 3. So today 3, 3, 3, 3. Then if you take the next one, it is 1, 2, 3, 1, 2, 3. Then 1, 2. It is 1, 2, 1, 2, 3. Then 1, 2. Then 1, 2. Then again 1, 2. Here it is 2. Then 1, 2. It is 2. So here how many 2? 1, 2, 3, 4, 5. 5 twos. So here it is 2, 2, 2, 2, 1, 2. Here 2, 1, 2, 1, 1, 2. Then here is also 1 and 2, 3. Here it is 3. So here it is 1, 2, 3, 4, and then 3 is 1, 2, 3, 4. It is 4. So the degree sequence also same for both the graph. Then length of the cycle, we'll just check out length of the cycle. What will be length of the cycle for this? So yeah, length of the cycle. If I take from here, it is 1, 2, 3, 4, 1, 2, 3, 4. Okay. Then if I take from here 1, 2, 3, 4. Here also I have 1, 2, 3, 4. Then if I take this 1, 2, 3, 4, I can take here 1. But here it is not same, na? I can take this here. Here it is 1, 2, 3, 4. Cycle is 4. But here I have only 1. If I take 2, 3, 4, 5, 6. So 6 here we have only 1, 2, 3. If I take the other one, 1, 2, 3, 4, 5, 6, 7, 8. So here it will be 8. So the length of the cycles are not same. Okay. It is not matching, therefore it is not an isomorphic graph. Okay. Then moving with the connected graph. What is connected graph? Connectivity is nothing but if there is an edge between two different vertex, then it is called as connective graph. There should be a path between every pair of the vertex. It's called as connectivity, connected graph. Disconnected means if there is no edge between the two paths, it is called as disconnected graph. If there is no edge between two vertex, is called as disconnected graph. Then cut vertex is nothing but a single vertex who removal disconnects the graph. If there is a vertex and I remove that vertex, and then it is called as cut vertex. We are just removing one vertex to disconnect the graph. So anything we can remove so that it will get disconnected. So here it is, you have here one, we am just removing that part from here, and then I'm removing these two edges so that it will get disconnected. Okay, we can remove one edge and more than one edge to disconnect the graph, is called as cut edge. Then cut vertex, then it is cut edge is what? It is a bridge. If you remove the bridge from the two vertex, then it is called as cut edge. If you are removing this edge in the graph, then it is called as cut edge. Okay, a removing of edge from the graph result into two or more graph, then it is called as cut edge. Then next one you have cut edge bridge. So here if it is connected, if the graph is connected and we remove this path, that is if I remove this and this, then it is called as cut bridge. What is a cut bridge? If deleting a certain number of edges from a graph makes it disconnected, then it is called as cut set of a graph. We can remove some vertex from the given graph, then it is called as cut set of a graph. Then you have edge connection. Connecting the two edges. If you connect any edge in connecting the edges to make it as a complete graph is called as edge connection. Then vertex connection, connecting any vertex to make a graph as a complete graph is called as cut vertex. Then you have Euler graph. What is Euler graph? A Euler graph is a connected graph which has a even degree. So the all the knots should have even degree. So it is A to B to C is 4, E is 2 and D is 2. So here degree is 2, B is 2, C is 4, it is 2, it is 2. So all these are even. No? If it is having even degree, it is called as Euler graph. Then you have the next one, you have A is 2, B is 3, C is 2 and D is 3. So you have 2, 3, 2, 3. So here it is even, odd, even, odd. It is not a Euler graph. If all the vertices are even, then it is Euler graph. So here you can take the other one also. Here we can take A is 2, B is 4, C is 2, D is 2, and E is 2. So it is 2, 4, 2, 2, 2. All are even. All are even. Therefore, it is a connected, that is Euler graph. The next one you have 1, 2, B is 1, 2, 3, 4, C is 1, 2, D is 1, 2, 3, 4, E is 1, 2, and F is 1, 2. So it is A is 2, B is 4, C is 2, D is 4, E is 2, and F is 2. So all are even, therefore it is also a Euler graph. What is Euler graph? Euler graph is nothing but the degree of the graph should be, every vertex should be even degree. Then Euler path. What is Euler path? Euler path as a Euler walk or a trial. The definition of the Euler trial or Euler path is defined as if there is a connected graph with a trial that has all the edges of the graphs, that the type of trial will be known as the Euler trial. So here it is like if more than two vertices of the graph contain the odd degree, then that type of graph will be known as the Euler path. If more than two vertex of a graph contains the odd degree, then that type of graph is called as Euler path. Okay. For example, you have here, you can take 1 and 2, here 1, 2, 3, here 1, 2, and here 1, 2, 3. So you can see here, two or more than two vertex has odd degree, then it is called Euler path. You can take this 1, 2, 1, 2, 3, 4, 1, 2, 1, 2, 3, 4, 1, 2, and 1, 2. So this is we cannot take a, it is a Euler path, but if it is connected, if it is having more than, then you can take the other one, does not, here 1, 1, 1, 2, 3, 4, and 1, 1. So here it is not, here you have 1, 1, 1, 1, and it is 4. So it does not exist. Okay, Euler path does not exist. This is a Euler path. Here 1, 2, 3, again 1, 2, 3, then again 1, 2, and again 1, 2. It is a Euler circuit. Here circuit does not exist. Okay. So here, what is mean by Euler circuit? Euler circuit which describes if there is a connected graph with a circuit that has all edges of the graph, then that type of circuit is known as Euler circuit. Okay. If all the circuit that has all the edges of the graph, that is a type of a circuit. It is in the type of circuit. It is called as a Euler circuit. So, trial consists of same vertex at the starting and ending of the trial. Then the type of the trial will be known as the Euler circuit. So you can read this as a point. If an Euler trial contains the same vertex at the starting and ending of the trial, then the type of trial is called as Euler circuit. Then you have what is a Euler circuit. So here they have given, here it is the degree is 2, here it is 1, 2, 3, 4, here it is 1, 2, here it is 1, 2, 3, 4, then here it is 1, 2. So yeah, we are just moving on. How to identify it is a Euler circuit? It is just moving from one point to other, that is starting and ending point should be same, that is we start from A to B, B to C, C to D, then D to F, F to B, then again B to E, then E to D, and then D to A is called as a Euler circuit. Application of Euler circuit, you have Euler path is a traverse each edges exactly once, but the starting and ending ends at the different vertex. With a Euler circuit, start and end at the same vertex. Euler path exists if exactly two vertex has odd degree, while Euler circuit requires all vertices have to be even degree. It used in the postal delivery, street swapping, transportation networks, and utility grid inspections to optimization routes within the redundancy. Then you have Hamilton graph. What is mean by Hamilton graph? A graph which is said to be Hamilton graph if there is a close walk in a connected graph which passes each and every vertex of the graph exactly once. except the root vertex and starting vertex. Except the end and the starting vertex should be same. That is A to C, F to E, E to D, D to A, and D to B, C to B, and B to A. So it's called as Hamiltonian graph, where it should pass through all the vertex, but starting and ending vertex should be same. Then you have Hamiltonian path. What is Hamiltonian path? If a connected graph, if there is a walk that passes each and every vertex of a graph only once, this walk is known as Hamiltonian path. Then what is Hamiltonian circuit? If in a connected graph, if there is a walk that passes each and every vertex of the graph only once, and after completing the walk return to the same vertex, then it is called as the walk, which is known as the Hamiltonian circuit. So yeah, next one you have is, so these are some example, that is it's starting from A to B, A to B, B to C, C to D, C to D, D to E, and E to C. Again, I'll just do it again for you. It's like A to B, B to C, C to D, D to E is called as Hamiltonian path. Here, it does not exist. Okay. The next one is E to A to B, B to C, C to D is called as Hamiltonian path. Then here, circuit is A to B, B to C, C to D, D to E, E to A, E to E. Then yeah, it is does not exist. Hamiltonian does not exist, and here also it doesn't exist. Okay. So here next one, Hamiltonian important properties of Hamiltonian graph. Hamiltonian graph, all edges or may not be covered, but edges must not repeat. In edges should not repeat here. Then Hamiltonian circuit can be converted into Hamiltonian path by removing one of its edge. Every graph that contains Hamiltonian circuit also contains the Hamiltonian uh, Hamiltonian path, but vice versa is not true. Hamiltonian circuit can have Hamiltonian path, but Hamiltonian path cannot have a Hamiltonian circuit. Then you have, there may exist more than one Hamiltonian path and a Hamiltonian circuit in a graph. It's not necessary there is only one Hamiltonian circuit or graph, it can be more than one. Then you have some rule called as Dirac theorem. If G is a simple graph with n vertices, n should be greater than or equal to 3 such that the degree of the vertex, every vertex in G is at least n by 2. Then G has an Hamiltonian circuit. Then Earth's theorem says, if G is a simple graph with a vertex which is n is greater than or equal to 3 such that the degree of U plus degree of V for every pair of non-adjacent vertex UV in a G, then it is G has a Hamiltonian circuit. So these are the two important theorems of your Hamiltonian graph. Then you have Euclidean and Hamiltonian digraph. Digraph means directed graph. So here, digraph is a short form of directed graph, and it is represented as vertices, nodes, and arrow called as a ray going from vertex to vertex. So here, Euclidean digraph is a connected graph where every vertex has in degree equal to its out degree. If in degree is equal to out degree, then it is called as Euclid digraph. A connected digraph is said to be Hamiltonian graph if graph contain a cycle that itself contain all the vertices in graph. This cycle is called as Hamiltonian cycle. So you can see here you have from A to B, then a B to C, C to D, and then D to A. That is a cycle. So here you can see, here you have 2 for 2 in degree, and here also for 2, here also we have 2, here also we have 2, and here it is 1 2, 2 is going out, 2 is coming in, therefore it is called as non-Euclidean. Here you can see 4 you have, so here it is 1 1 going out, 1 coming in, 1 going out, 1 coming in, 1 going out, 1 coming in, 1 going out, 1. Here also you can see one is going, two is going outside, and one, two is coming in and two is going out. It's called as euglary. Then you have next one is application of Hamilton. It is used to find the circuit that visits every road intersecting in a city. Each place pipelines intersect in a utility grid. Each node is communication network exactly once. The famous traveling salesman problem is also an example for Hamiltonian graph. Next comes the planar graph. What is mean by planar graph? A graph that's said to be planar if and only if it draws up in a plane such that no two edges cross each other. So if it is crossing, it is called non-planar, and if you remove the line and pass it on from other edge, other side, that is a non-planar graph can be converted into planar graph. Okay, how you will be converting? We can remove one edge and we can connect it from the in a other way. Then it is called as planar graph. So every time we can convert non-planar to planar graph. Okay. So these are some examples where it is converting non-planar to planar graph. Then you have important properties of planar graph. So here some of the important properties are: if you have a graph with a edge R, edge E and region R, then R should be always greater than or equal to 2 by 3 E. If it is a connected planar graph, then with a vertex and edges E, vertex V and region R, then V minus E plus R is equals to 2 will be a complete graph, that is planar graph. Then a connected planar graph will be with E and vertex V will be given, and E 3V minus E is greater than or equal to 6. A complete graph Kn is a planar if and only if n is greater than 5. The complete bipartitional graph KMN is a planar if and only if m is less than 3 and or n is less than 3. Then if any planar graph, sum of the degree of all vertices equals 2 into total number of edges in the graph. If G is a planar graph with a k component, we can write R is equals to E minus V plus k plus 1. Then if any planar graph, sum of the degree of the region will be equal to 2 times of total number of edges in the graph. If any planar graph, if the degree of each vertex, each region k is given as k into